Page 19. Okay, so here's example one. We're going to be exploring logs and exponentials of other bases. But a lot of things will still look similar to each other. So here's example one here. If 3 to the x is equal to 1 over 81, if it was e to the x, I will take the natural log of both sides. But here, I can take log base 3 of both sides because I know that logs and exponentials will cancel each other out. So if I do this, log base 3 of 3 to the x is equal to log base 3 of 1 over 81. Just like how natural log and exponential base e cancel each other out, logs of base 3 will cancel out with exponential base 3. Right? So also the x will come down in front because this is part of a log property. So log properties are not just restricted to just natural log. It can be logs of other bases, log base 2, log base 5, log base 7. They all share the same properties. So this x comes down. We know log base 3 of 3 will cancel out. And if I can somehow get the two bases to match, I can also clean this up as well. Now, 81 is the same thing as 3 to the 4th. If I continue cleaning up, I can make this 3 come up to the numerator to make it 3 to the negative 4. And now I have another property available to me. I'm inside a log expression. That negative 4 can come down in front. And now log base 3 of 3 cancels out. So x equals negative 4. So natural log and exponential base e cancels out. Log base 3 and exponential base 3 cancels out. Log base 5 and exponential base 5 cancels out. Number 2. Yesterday, we did a problem similar to this. Yesterday, it was maybe a problem like this. Natural log of x minus 4 is equal to 8, right? We know this is log base e. If I want to undo natural log, I can involve exponential function base e, raise both sides with e as the base, and that cancels out. Same thing here. Instead of base e, this is base 2. So if I want to cancel out log base 2 to get into the x, I can raise both sides with 2 as the base. Same idea. E and natural log cancels out because natural log is base e. 2 and log base 2 cancels out because they have the same base. So x is equal to 2 to the negative 4, which is 1 over 16. If you can cross off the derivative rule for other bases, I want to present a better uh, uh, way of representing my rules here. So I'm going to have us write this here. So derivative rules for logs. Now, log functions will fall under two categories, either base E or base A. Base A will just be other bases, base 2, base 3, base 5. They all have a similar formula. So I'm going to differentiate between these two here. Natural log is kind of like the parent base because it's the cleanest of the derivative rules. And we know the derivative for natural log is just u prime over u. So this is base E, right? Base E is log base E. We get just u prime over u. So ln is a shorthand form of writing log base E. But let's say it was base 2 or base 3 or base 5, then we'll say log base A of u. And that A can mean any base. It can mean base, yeah, like I said, any integer, positive integer base. So I want to indicate or show that it's essentially the same thing as u prime over u, with a little bit more conversion that needs to occur. So to the I'm going to leave some space here, but it's basically still u prime over u. So I want us to just understand that, okay, log base A, natural log, it's the same thing as u prime over u, but it's not base E, so there's conversion that has to happen. And that conversion is going to look like 1 over natural log of A. It's basically having to go through a change of base before turning itself into base E, and then that way it can just match the rule above. And A is whatever the base we're dealing with. If it's base 2, then it'll be 1 over natural log of 2. If it's base 5, it'll be 1 over natural log of 5. It's just going to be some coefficient that's going to land in front of your derivative. Okay. So let's do a quick example before we look at some of the more complicated ones. So for instance, if I want to find the derivative of log base 3 of 4 minus x squared, I'm going to essentially understand, okay, it looks complicated, but it's basically natural log with a little bit of extra in front. So log and natural log have a similar form. We have to go through a little bit of conversion here. So we start off with what? 1 over ln of what? 3. Basically getting it into a natural log form. And then the rest looks just like natural log of u prime over u. What's u prime? Negative 2x over the u value. The original, right? So 4 minus x squared.
If she's here.
Exactly.
Oh,
Thank you.
thank you.
Any questions here? All right, so let's look at example 3. Find f prime Now, whenever you see a log of other bases, I know it looks more intimidating because it just looks like it's a lot more complicated than natural log, but let's just pretend like we're dealing with natural log, right? If it was a different problem, let's say it looked like this, natural log of cube root of 2x squared plus 7. What would you do first? Okay. You would use some properties, right? Or how would you rewrite this? 1/3, okay. And then what would you do with that 1/3? Yeah, coefficient, right? So same thing here. So whenever you see a log problem, just treat it like natural log, and then And then once you get it all the way cleaned up, then you can think about the derivative rule, right? So just for the most part, just treat it like natural log, but then at the end, there's going to be a slight conversion. But I don't want us to feel like, oh, this is a brand new problem. I don't know where to start it. Treat it like natural log, and it'll get you most of the way until the very end. So. Okay, bring the 1/3 down. Again, we're going to treat it like natural log. We know the 1/3 will stay. We know there's a u prime over u, but then that log 5 is a little bit extra, and that little bit extra that's the only thing that's different about log base a. There's just that 1 over natural log of a that's in front, but we expand it the same way. We treat it the same way. The beginning is the same. The ending is nearly the same with just a little bit of adjustment. The y prime is equal to 1/3. We have u prime over u, but we got to take care of that log base 5. So 1 over natural log of 5. And the rest feels like natural log. U prime over u. Okay, number 4. Again, pretend this is natural log. What would you do first? Expand, right? Quotient property. Log of a over b, or natural log of a over b is just natural log of a minus natural log of b. So we'll just treat it like natural log until the very end. Continue expanding. We can't we could expand that 5x cubed, but I wouldn't expand this because this is already a fairly easy u value. But I do want to expand that. I don't want to have to deal with this whole thing as my u value. So I want to bring that 3 down, but I don't think it's worth the trouble to expand the 5x cubed. Oh, make sure that we don't treat this like power rule. We don't want to bring the 3 down and make this squared, right? This is not derivative here. We're just bringing that exponent down. So I see some students trying to merge this with power rule for derivatives, and they're different things, right? We're bringing the 3 down as a way of cleaning up. It's not a derivative process. Now there's a hidden base here. What's if you see a log with a base, what's that hidden base there? 10, yeah, it's base 10. Because natural log and log are, or log base 10 and log base e are used the most often. They have a shorthand abbreviation for them. So log base e is natural log, or ln, and log base 10 is just log. So we'll treat this like u prime over u with a little bit of adjustment with that log base 10. So 1 over natural log of 10 is the adjustment, and then should feel like natural log, u prime over u. The 3 is a coefficient that stays. Log base 10 will experience a conversion as well. And u prime over u. You can leave your answer unsimplified, that's fine. Next page. I want to create a chart so that we can kind of see that there's 4 different rules here. There's also this a to the u one here. This is basically looking like e to the u. So we have natural log, which is base e. We have exponential function, which is base e. And then we just learned log base a, log of other bases, and also exponentials of other bases. So just want to do this so that we can kind of see some for comparison purposes. So I'm going to put this up here. Natural log of u will look a lot like log base a of u. Right? We talked about how natural log of u is just u prime over u. Log base a of u is also u prime over u, but with a little bit of extra 1 over natural log of a. Right? Okay. So I want us to see that connection between these two. They're essentially the same with conversion. Now, exponential function e to the u. What's the derivative of e to the u? We talked about this yesterday. E to the u is just what? Right, the original function, right? So e to the u is e to the u times what? Times u. So times u times what? Times u prime, right? So e to the u is just the original function times the exponent's derivative, right? This is base e. Now, what if it was exponential function base 2? What if it was 2 to the 3x, or 5 to the 6x, or 6 to the 8x? Then we have a slightly different formula. It's still an exponential function, but it's no longer base e. It's base a. So base 2, base 3, base 5, they all fall under a different category that we call base a. So the derivative for a to the u, this is exponential function base a, constant raised to a variable. I want you to leave a little bit of space, but it's essentially the same as above. It's the original function times the exponent's derivative. So original function times exponent's derivative. But the conversion that has to happen, we got to convert it into base e, and it's going to look like this, natural log of a. So for natural log, it's 1 over natural log of a for the conversion into base e. And then for exponential function, if I want to convert it into base e, it's just natural log of a times, and then it follows the same format. It's the original function times the exponent's derivative. Now, memorizing these rules, I think sometimes students get a little bit thrown off, like, wait, where does the natural log of a goes? I don't remember whether the natural log of a is in the numerator or whether it's in the denominator. So the way that I remember it is I look at the rest of my rule here. If I see a denominator presence with my parent rule, then that reminds me, oh, there's natural log of a that's going to go in the denominator. Here, my rule doesn't have a denominator presence, so that helps remind me, oh, my natural log of a will go in the numerator. Okay. So if I see a denominator in my original rule, that helps to remind me that, oh, my natural log of a is in the denominator. So it says find f prime for the function 5 to the x squared minus 2x. I want us to think of this as it's essentially the same form or the same similar rule to e to the x squared minus 2x. I want us to see that connection, that 5 to the x squared is in the same category as e to the x squared. They're both exponential functions. So if we treat it like, okay, I'm just going to follow the same rule with a little bit of adjustment, then I find that to be a little bit easier to think about, right? Because we know that e to the u, which is e to the u times u prime. So a to the u is just the original function times the exponent's derivative. So I'll leave some space in front. but it's essentially, it's going to be the same as e to the u. It's the original function times the exponent's derivative, so times what? 2x minus 2. But because it's not base e, I need a bit of conversion in front, so what do I need to multiply by? Natural log of 5. There it is. And natural log of 5 is just some coefficient that has to be in front as a way of converting it into base e. Okay, example 6. Find f prime for x times 4 to the negative x. We obviously have to apply the exponential rule for 4 to the negative x. But what else is going on? What else do we need to involve? How many terms do you see there? Product rule, yeah. Again, we'll treat 4 to the negative x the same way or similar to the way that we treat e to the negative x. We know e to the negative x would just be e to the negative x times negative 1. So 4 to the negative x is just 4 to the negative x times negative 1 with a little bit of conversion in front. Thanks. So that conversion is going to look like natural log of a. Sorry, natural log of 4 in this case, sorry. And then the original function times the exponent's derivative. Okay, any questions? All right, so let's do our homework will be page 21 and 22. I'm going to work with you on the odds. And then if we can get through the evens, that's great as well. But I'll work through the odds so we can kind of see one of every type. And then whatever you don't finish, you can just focus on the evens. But I think we can probably get through the whole thing class. So page 21, 22. So the log base a of u, I like to write it this way. If you want to write it this way, you can. I like to think of it as looking exactly like my natural log rule, just with 1 over natural log of a in front. So I like to think of it this way. 1 over natural log of a times u prime over u. And then a to the u is just essentially the same thing as exponential base e, the original function times exponent's derivative with a little bit of extra in front. So 5 to negative 4x. Let's understand it's going to be in that family of e to the negative 4x. So we'll treat it the same way. The original function times the exponent's derivative with a little bit extra in front. Okay, 41. Again, we have to go through what rule to get to our derivative. Product rule. Okay, try that. 49 log base 5. I know sometimes we look at this, it feels more intimidating than natural log, but just pretend like it's natural log until we get to the derivative, right? So what would you do first if this was natural log? Yeah, move that exponent down. And again, if we still pretend like it's natural log, you would just say u prime over u with coefficient in front, but you know there's something a little bit extra with that log base 5. And that the slightly new thing we got to do is include that 1 over natural log of a to handle that log base 5. But everything else will feel just like natural log. Okay, try 51, 53, 55. You're going to be expanding or applying log properties, right? You're applying log properties for each of these before you explore your derivative rules. For 55, I just want to remind us, if I have multiple parts in my log expression, let's say I have log of a times b over c, or natural log of a times b over c, I can always rewrite that as log of a plus log of b minus log of c. So basically, the big picture is anything that's in the numerator is part of a positive log term. Anything in the denominator will just be part of a negative term. So again, I'm just treating this like natural log in terms of expansion. So we'll do u prime over u with a little bit of extra in front. We'll do u prime over u here as well within the conversion. What's going to happen here, though? What is this? Yeah, this is just constant, right? There's no variables here. So we know this will just wipe out to 0. So we only have to worry about derivatives for these two terms. So u prime over u with a little bit of extra in front. Okay, I think, sorry, yeah, we've done the implicit on the next page, so let's spend 5 minutes or 5 to 10 minutes, see if we can get through the rest of the homework here. So 40 to 56. Go ahead and try those. I can also put the answer key up as you guys are working through it. So don't worry about page 22. We'll just do page 21. Okay, so we finished this page. So this is basically your homework. Tomorrow I'll just be checking page 21. So I think most of you guys have finished your homework. Now, tomorrow we're going to start our quiz review. We've covered all the topics that we need to cover. So tomorrow we'll start our quiz review. We'll do review Monday, Wednesday, Thursday. So plenty of time. Our quiz is next Friday. Okay. All right, come get your phones. Yeah, no 22, just page 21.
I turned in my homework today.
Okay, great. Let me see. Okay,
So
great, thank you.
I like this one. Why don't you move the cube down?
I could. I just figured that x squared is easy enough where I don't have to go expansion.
Oh, okay.
Yeah. But if you bring it down versus not bring it down, you'll get the same.
Just a little bit simplified because it'll be one.
Slightly simplified, yeah. Yes.